A very good morning to all of you. Today I am going to start about this multi-compartment open model. This is under unit number 4 under pharmacokinetics, right? Till now we have seen about one compartment open model, but this is multi-compartment open model. What are the topics you are going to read under this multi-compartment open model? Two compartment open model, IV bolus, then IV infusion and oral administration. Oral administration is also called as extravascular administration. So you have to read about all these four topics in detail in this multi-compartment open model. This is also called as delayed distribution. Why it is called as delayed distribution? See ma'am, in case of one compartment open model, your drug entry and exit will be happening from central compartment. See, this is like your one compartment open model. This is the compartment, that is nothing but central compartment. Here you have blood and other body tissues, right? So here what is the process? Here we have an absorption and here we have an elimination, right? So this is all about your one compartment open model. So in case of IV bolus injection, we are neglecting this absorption. So we are considering only elimination, right? So one thing you have to remember, in case of one compartment open model, your drug distribution and elimination will be happen through this central compartment. Here there is no attachment of any other peripheral compartments. Only we are assuming our total body as a single uniform compartment, that is of your one compartment open model. And in case of multi-compartment open model, here we are going to learn about more than one compartments. That means our body is having more than one, that is one central compartment, and this central compartment is joined to that peripheral compartment. So your peripheral compartments may be either of 2 or 3 and etc. Okay, so why this delayed distribution was happening here multi-compartment model? See, in this central compartment, the highly perfused tissues will comes, and in peripheral compartment, those are poorly perfused tissues, right? So from this central to the peripheral, it will take some long period of time. Why? Because here there is a presence of more than one peripheral compartment, and in case of one compartment we have only one compartment. Our total body has a acts as a one compartment. So for that reason, in case of one compartment open model, we have selected that rapidly absorbed drugs. So I already told you while discussing this one compartment open model, this model fits or suits to rapidly absorbed or rapidly distributed drugs. That means the elimination or distribution or excretion phenomenon will be happen very rapidly. And in case of this multi-compartment model, it will take some time to travel from the central to the peripheral. Traveling is nothing but the drug distribution. So that's why it is also called as delayed distribution models. In one compartment open model, the drug is distributes only in the central compartment. Am I right? Here, in case of one compartment, you have to remember the central compartment. It will plays an important role for the drug entire physicochemical ADME processes. For IV bolus administration, this is also belongs to this one compartment open model. See here, for IV bolus administration, drug distributes to some tissues which are not highly perfused with blood. Then the distribution takes time to get equilibrium between the blood and tissues. See, Once the drug will attains the equilibrium between the blood and the tissues. So after taking a dosage form through the IV bolus or IV infusion, where it will get equilibrium? It will get equilibrium within the blood as well as with the tissues. So it will take some time to get equilibrium between the blood and tissues. Why it will take some time? What are the reasons it will take some time to reach its equilibrium? What are the possible parameters it used to get some delaying of time? Distribution of drug from the central to the peripheral compartment and elimination of drug from by the central compartment. See, in this multi-compartment open model, this is central and this is peripheral. Okay, see ma'am, in case of one compartment open model, you have to remember only about central compartment. Here, all the parameters is happening only through the central compartment. There is no peripheral, only one compartment, right? Here in case of multi-compartments, we have a central compartment. This will be attached to this peripheral compartments. That means the drug absorption, distribution is taking place from the central to the peripheral, right? So here we are observing that delaying drug distribution. Why it is happening? See, the distribution of drug is happening from central to the peripheral. See here, this is happening central to the peripheral. That is nothing but your drug distribution and elimination of drug from the central compartment. Okay, so the drug is transported or the drug is distributed from the central to the peripheral. Then there is no drug here. Okay, so there is a declining of plasma drug concentration from the central, but there is an increasing of plasma drug concentration in the peripheral. Why? The drug is transported from the central to the peripheral. So here central compartment is giving the drug to the peripheral, right? So then the elimination process is also happening from the central. So where the drug distribution starts, at that compartment only it will get eliminated out. Here in case of peripheral, only the drug distribution is happening. The elimination is occurring from the central. So you have to remember two things. Okay, the drug is distributed from central to the peripheral and the elimination was happening from the central compartment. Because of these two reasons, okay, there is a loss of plasma drug concentration in the central. Why? Because it is only involving the elimination and it is only giving its drug to the peripheral compartment. Then there is no plasma drug concentration or there is very less plasma drug concentration in the central compartment. Okay, then it means the decrease in the drug levels in the central compartment. So here we are telling orally. Then we can also describe by exponential equation. That means how it is practically happening. That means how the plasma drug concentration decreasing was happening practically. We can explain it by the exponential equation. This part of plasma level time curve is called as distribution phase. Then once equilibrium attained between the amount of drug present in the central and the peripheral. See, here we have a central, right? Here we have a peripheral. For example, in case of central compartment, you have 10 mg of drug. Total 10 mg of drug will be distributed to this peripheral. That is, here we have 10 mg. At that, after distribution, we don't have sufficient drug, we don't have sufficient plasma level concentration. Since here we are getting 0 plasma drug level concentration. But here what it is saying in this sentence, once equilibrium attained between the amount of the drug present in the central compartment and the peripheral compartment. See here. Here we are having 5 mg and here this it is transported 2.5 mg. Then after giving 2.5 mg, how much amount of the drug is left with this central compartment? Same 2.5 mg. Here we are getting equilibrium, right? We are getting equilibrium here. So once the transportation of the drug amount will be same in case of central and the peripheral. So then we are getting equilibrium. Then there is a decline in the plasma level takes place mono exponentially. This decline is only from the elimination of drug from the body. See, after some time, there is a decline in the plasma drug concentration. When you observe plasma drug concentration versus time profile, there is a decline in the plasma drug concentration after certain point. Why this decline is happening? This decline is happening because of elimination phase, right? This decline is happening because of elimination phase, not to that distribution phase. You have to remember. So the decline of the plasma drug concentration was happened only through the elimination phase, not to the distribution phase, right? Then more number of peripheral compartments will be equilibrate with the central compartment at different rates. More will be exponentials. That describes plasma level curve. See here, we are transporting our drugs to the n number of peripheral compartments. Okay, in case of one compartment, here we are transporting our drug only within the one compartment, that is nothing but central. So here we are able to get mono exponential forms. But in case of this multi-compartment open model, we used to get more number of exponentials in the equation. This more number of exponentials will describes you the plasma level time curve. After equilibrium of drug within the peripheral tissues, then elimination of the drug will follows first order kinetics. So here our drug is eliminated out from the central compartment, right? So here we have n number of peripheral tissues. So after attaining equilibrium with these peripheral tissues, the elimination of the drug will follow first order kinetics, that is concentration dependent. So the drug is following concentration dependent kinetics. The next part in this multi-compartment open model is two compartmental open model. See ma'am, once you learn the concept, it is very easy to describe the equations. That's why I'm stressing you. Okay. So two compartment open models. Here the drug distribution is happening in two compartments. Those are central compartment and the peripheral compartment. So you just assume your central compartment as 1 and your peripheral compartment as 2. Okay. So in this case of central compartment, which type of tissues are here? Blood and highly perfused tissues. And in case of peripheral compartments, you have poorly perfused tissues, right? So how the drug transfer will be happening in this two compartmental open model? See, we are assuming central compartment as 1 and peripheral compartment as 2. So the drug is distributed, that is the drug deposition phenomena, deposition. So which type of mechanisms are involved in this deposition processes? We have distribution, metabolism and excretion. All these three together called as deposition processes. So the drug deposition was happening between the central to the peripheral through this rate constants, right? So here the drug is distributed from 1 to 2 compartment. That's why the constant K 1 to 2. The K is rate constant, right? So and then The process is a reversible process. That is, the drug deposition processes are reversible. Then from the peripheral to the central compartment, the rate constant is 2 and 1. So K 1 and 2 and K 2 and 1. This is called model 1. And then you have a model 2. So in this model 2, we are introducing the K13, that is elimination process. See, this is wrong, ma. Your elimination is taking place from the central compartment only. Okay, so just observe, this is wrong. So your drug is transported between K1 and 2 and K2 and 1, and then you have a elimination KE. This elimination is happening from the central compartment. So your central compartment number is 1. And if you assume here one more compartment is there, then you may call it as 3. That's why the constant as K1 and 3. So the plasma concentration of a drug that will follows two compartmental kinetics. The decline in the plasma drug concentration is bi-exponential. See, when you observe the plasma level concentration versus time profile, after attaining certain point, there is a declining of your plasma drug concentration may be observed. So this will be due to deposition processes. What are the two deposition processes here? Distribution and elimination. Because of these two processes, there is a declining of plasma drug concentration. This decline will be by exponential. So here it will includes excretion and metabolism together called elimination. So majorly we are talking about two deposition processes. Then it will includes distribution and elimination. See ma, only the elimination process is taking place through the central compartment. After attaining this peak plasma concentration, there is a declining of plasma drug concentration may be observed. This decline may be due to the two deposition processes, that is distribution and elimination. So here we are going to calculate the bi-exponential plasma drug concentrations. Okay. Depending upon the compartment from which the drug is eliminated. So here we have two compartments, right? Central and peripheral. So that's why depending upon the compartment from which the drug is eliminated, majorly the drug will get eliminated from the central. Okay. And in some cases, in some exceptional cases, there is an involvement of peripheral also. Here also KE is there, but majority the drug will be eliminated out from the central compartment. So there are three types: two compartment open model with elimination from the central compartment, or two compartmental open model with elimination from peripheral compartment, and two compartment open model with elimination from both the compartment. See, majorly the elimination was happening from central, and in some exceptional cases it is also happening from the peripheral, and in some cases it should be happening from both the compartments. So there is a three cases. It will be depending upon the at which the compartment is involving in the elimination processes. And then the concentration of the drug in a compartment is assumed to be uniform in its volume of distribution. See, always we should need an uniform distribution of your drug within the compartment. That is nothing but your central compartment. So in that cases, this two compartmental open model is assumes that T is equals to 0. There is no drug in the tissue compartment. Initially, the tissue compartments are empty. There is no drug concentration in that. So at that time, the T is 0. After an IV bolus dose, so before an IV bolus dose, we don't have any concentration of drug in our central compartment. So after taking an IV bolus drug, definitely the drug levels will be higher in the tissue compartment, right? So initially it is 0. After taking an IV bolus, it will be increases. Then the concentration will reaches the maximum. See, then the concentration will reaches the maximum. Then after that, what is going to happen? After that, it will declining. See, initially there is no plasma drug concentration, then at the time 0. After the time passes, then after you taking and dose, that is nothing but your IV bolus dose, the drug levels will be increases with respect to the time. Here see, the time is also increasing here with respect to the concentration, the time is also increases. After certain point of concentration, if the drug reaches, then it will be declining. First, IV bolus administration. This is all the concept of multi-compartment open model is nothing but your two-compartmental open model. So, first you have IV bolus drug administration. So, how it will follows the pharmacokinetics and how the derivation will be. IV bolus administration. After the IV bolus of a drug, that follows two compartmental kinetics. The decline in the plasma concentration is by exponential. Why? Because here we are having two deposition processes. That's why it is called by exponential process. So that indicate the presence of two deposition process. Two deposition processes by exponential, distribution and elimination. You have three terms to remember. Then after some time, after taking an IV bolus, after some time, a pseudo distribution equilibrium is achieved. It is not a perfect exact distribution equilibrium. It is a pseudo. What do you mean by pseudo? Pseudo is nothing but an imitation. It is imitating just. Okay, it is imitating. Not it is an exact equilibrium. Which type of equilibrium it is? Distribution equilibrium. So after taking a drug after some time, so you will achieve some pseudo distribution equilibrium is achieved between the two compartments. Those are central and peripheral, which the subsequent loss of drug from the central compartment. So here there is a subsequent loss of your drug concentration. Why there is a loss? It is going to be eliminated out. The loss is nothing but the drug is going to be eliminated from the central. So the second slower rate process is called post-distributive or elimination phase. See here, nothing is there. Don't get confused. After some time, it will achieve pseudo distribution equilibrium between the two compartments, central and peripheral. So here the drug is getting eliminated out. So the concentrations of the drug in the central compartment is low, or there is a loss of drug is happening from this central compartment. This loss is happening due to the drug elimination. Then there is a second slower rate process after this post pseudo distribution equilibrium. Then your graph will be like this. Then it is called as post distributive or elimination phase. Here we are getting post distributive or elimination phase. Okay. Then the elimination from the central compartment. How the figure will be. See, central compartment, peripheral compartment. We have K12, K21 and K13. Here elimination is going. Then what are the parameters we need to consider? If the elimination is happening from the central compartment, so what are the parameters we need to follow? After the IV bolus of a drug, that decline in the plasma drug concentration is by exponential. Then the two deposition processes are distribution and elimination. These two processes are only evident when you plot a graph, on semi-logarithmic plot, T versus T. C versus T, plasma drug concentration versus time profile. When you plot the graph on semi-logarithmic plot, you will get these two processes, distribution and elimination. Initially, the concentration of drug in the central compartment, the drug in the central compartment will be declines rapidly. It will be due to the distribution of the drug from the central to the peripheral. This is called distributive phase. So when the drug is distributed from the central to the peripheral, this is called as drug distributive phase. See here, this plot will explains you the changes in the drug concentration in the central and the peripheral after an IV bolus dose, which will follows the two compartmental open model. So if the drug will follows two compartmental open model, when you take such kind of drug through the IV bolus injection, so the plasma drug changes was happening between the central and peripheral will be explained extensively through this graph. Once you observe this graph, it is very easy. When you plot a graph between the time versus log concentration, this plot was made in semi-logarithmic graph, semi-log graph, not a Cartesian graph. That's why
Madam,
we are directly taking log drug concentration values. In case of Cartesian graph, in case of normal graphs, here we are taking only the concentration values, right? So in case of semi-logarithmic graph, we are directly taking log drug concentration values. And then the graph will be like this. What it is exactly. See ma, this bottom curve will indicated you the peripheral compartment and this top curve is central compartment. See, when you take an IV bolus drug, initially rapid decline of distribution phase was observed at this point. Initially, there is a rapid decline of the distributive phase. After distribution, it will goes elimination, right? So, there is a slow terminal decline in the elimination was observed here. So, here the distribution and the elimination, both the phenomenons are happening through the central compartment. Okay. So here the y-intercept is 1 by Ke, 1 by elimination rate constant. So once you remember this graph, the derivation part is very easy. Then according to the mass balance equation, your derivation came. Okay. According to the mass balance equation, the derivation for the drug which follows the IV bolus administration when it will be given through the two compartmental open model. Everyone has to write this equation. X naught is equals to XC plus XT plus X3. Xc is the amount of the drug in the central compartment. That's why C. C means central compartment. X means amount of the drug in the central compartment. And Xt is the net balance of rate input. Net balance of rate input. And X3 is the output. So, where we are getting output? From here. That is nothing but central compartment. We are getting output here. That is nothing but elimination. So that's why here the constant is K13. Right? And then see, you always calculate the rate of change. You always calculate the rate of change of the amount. So that is nothing but dxc by dt, rate of drug amount change in the central compartment, rate of amount change in the central compartment. That is nothing but dxc by dt, right? That is equals XC means what? Amount of drug in the central compartment. amount of drug in the central compartment, that is K21XT minus K12XC. First you write down, next I will explain you. Then K13XC. So here we are calculating our rate constants in terms of amount of drug available in the central compartment, right? So in this amount of drug available in the central compartment is nothing but XC. So rate of input is happening from peripheral to the central, K21 here. So that's why rate of input is K21. Sorry, rate of amount of drug in the central compartment is K21XT. XT is, you're always talking about the amount of the change in the drug concentration with respect to the time. Okay, so here the rate of input is K21XT and then K12XC. 1 to XC. How it will comes? 1 to XC. XC is the amount of the drug in the central compartment. So 1 to 2. How much amount of the drug is available from 1 to 2 compartment? Then 1 to 3 is elimination. That is clear. So that's why how much amount of the drug will be remained in the elimination process and how much amount of the drug will be remained in the net balance of rate of input. So your basic equation will be like this according to the mass balance equation. So here you have two methods to calculate this two compartment IV bolus administration. This is one method, that is according to mass balance equation. First you have to remember this equation, then you have to remember this basic equation. This is the basic. Then you can calculate all the derivation part from this basic equation. dxc by dt is as it is. Then K21xt. Here xc are the common. So that's why you can extract this xc. 1 2 plus 1 3. Minus into minus plus here. So that's why you will get plus here. Then the differential equation is describing the rate of change of drug levels in the tissue compartment. The differential equation describing the rate of change of drug levels in the tissue compartment. Then the equation will becomes, here there is no elimination. We are talking about the tissue compartments, that is nothing but peripheral here. So within the brackets you can write down the tissue compartment is nothing but peripheral compartments. That's why in this equation there is no 1 3. That is, there is no 1 3, that is of belongs to elimination. So the equation is K12XC, K21XT. So 1 to XC, here 1 is peripheral and 2 is 1 is central and 2 is peripheral, right? So here K12 and here K21. Here we are writing K1 and 2. That means the drug plasma level concentrations will getting changed from the central to the peripheral. So that's why K12XC minus K21XT. So with respect to the time, the plasma drug concentration will be changes from compartment 2 to the 1, peripheral to the central. So your equation is K12XC minus K21XT. Then the rate of elimination. So you just forget about all this XC. You have to focus only on elimination. The rate of elimination of drug from the central compartment is given by dx3. Here we are considering third compartment for our drug elimination. That's why dx3. Then divided by dt is equals K13XC. Here we are getting elimination process with respect to the plasma drug concentration level. That's why K13 xc. Then we need to do some integration from 0 to t and then t to t. 0 to t dx3 is equals integration of 0 to t. Here this is a constant k13 xc into dt. Then then x3 is equals, we need x3, right? Then k13, this constant is always before that integration part, right? 0 to t. Then x into c dt. See, we want x3 here. Then this is a constant, that's why we brought here. Then integration from 0 to t, xc into dt is common. So this is the value of, what is that? x3. So then you have to substitute this x3 value in the first equation. What is the first equation? X naught is equals xc plus xt plus x3. So you need to, what is that? You need to substitute this x3 value in this equation. Then you will get the equation like this. x0 is equals to xc is common, xt is common. Instead of x3, k13 integration 0 to t xc dt. After that, you have to rewrite this above equation. How you can rewrite this? You can take it out this xt. Then x0 minus xc minus of k13 integration of 0 to t xc into dt, right? Then after this rewriting this above equation, you have to substitute this xt value in the equation 2. What is our equation 2? This is our equation 2. See, this is our equation 2. You have to substitute this xt value in this equation. See, xt value in this equation. So once again I have written this equation 2 here. Okay, I will stop here. In the next class I will continue this derivation.